In this lesson, I want to talk about linear systems. A linear system is a finite set of linear equations. So, for example, if I have 4x1 minus x2 plus 3x3 equals 1, negative 1, then that equation by itself, even though it's a single linear equation, that equation is a system of linear equations. Now I am going to write a second one. 3x1 plus x2 plus 9x3 equals negative 4. And so this is a system of two linear equations. There are a total of 2 equations and 3 variables, 3 unknowns. Now, what would a solution to this system look like? Well, it would be a sequence of 3 numbers. For right now, we'll call them S1, S2, S3. A sequence of 3 numbers that satisfy both equations, and that's key. Your solution has to satisfy all of the equations in the system. If it only satisfies one of them, if it only satisfies a few of them but not all of them, then it's not a genuine solution. So let me give you one solution to this system. One solution to this particular system would be x1 is equal to 1, x2 is equal to 2, and x3 is equal to negative 1. That would be one solution to this system right here. Okay, well, not all equations have solutions. Not all systems have solutions. So, what would be an example of something that doesn't have a solution? Out of those 2 systems that I've just written, which one of them there does not have a solution? It would be this one right here, the one that says 2x plus 3y equals 6 and 2x plus 3y equals 8. That does not have a solution. And the reason why is because this is a set of 2 equations, 2 linear equations, that have exactly the same slope but different y-intercepts. So if I solved for y in the first one, it would be y equals negative 2/3 x plus 2. If I solve for y in the second one, it would be y equals negative 2/3 x and then plus 8/3. And so same slope but different y-intercepts. And so this system here is said to be inconsistent. Inconsistent. But even though the slopes are the same, the y-intercepts are different, and that means that the 2 equations themselves are fundamentally different. So, even though the system's inconsistent, we also say because the equations are different from each other, then the system is independent. Independent. Independent means that no equation depends upon the other. Now, in this one right here, you can see that the second equation is just 2 times the first equation. So really, this system has infinitely many solutions. And all it means to be consistent, all it takes to be consistent is that you have at least one solution, and this system here has infinitely many. So we would say that this is a consistent system. Definition of consistent means at least one solution. But we would also say that this system is dependent. And the reason being is because if I take the second equation here and divide everything by 2, then I get the first equation. And so one equation is just some multiple of another equation. So it's dependent. So they're the same line, basically. So, okay. Consistency, inconsistency. Dependency, independency. All right. Let's go ahead and look at a scenario. So let's say I have 3x plus 5y equals 8. And let's say I have 3x minus 5y equals negative 2. Well, go ahead and pause the video. See if you can determine whether the system's consistent or inconsistent, dependent or independent. So this particular system is both consistent and independent. We can use the elimination method from Algebra 1 and eliminate the 5y by adding the two equations together. So we get 6x equals 6, which means x equals 1. And then when we substitute x equals 1 back into any of the equations, we also get y equals 1. And that means at least one solution exists. And so this system is consistent. The system is also independent, because if I solve for y, in the first one I get negative 3/5 x plus 8/5. And if I solve for y in the second case, I get 3/5 x plus 2/5. Notice the slopes of the two linear equations are totally different. And so that means that the two lines have to cross at a single point. So what we have here is consistent and independent. Now remember, a linear equation can have more than two variables, but the two-dimensional analog works pretty good. And by the way, this works for all linear systems that have more than two variables as well. So we'll call this one right here, that's a really bad x-axis, by the way. We'll call this scenario 1. Okay, scenario 1. Scenario 1 is that you have two lines that meet at some point. And so this particular system is both consistent, because it has at least one solution. And visually you can see that the two lines are totally different from each other. And so this is independent. Consistent, independent. Okay, scenario 2. Scenario 2 is when you have two lines, but the two lines turn out to be parallel. So we've got a line here, and we've got a line here. And so the lines never meet, so there is no solution. So that means that the system here is inconsistent. But the two lines are different from each other. They're not the same line. And so while the system's inconsistent, it's still independent. And lastly, we have situation 3. Situation 3 is when you have the same equation. So one just falls right on top of another. Now this system has infinitely many solutions, and remember the definition of consistency is at least one. So this system is consistent, but since both equations end up being the same equation, we have dependency here. And so this system is dependent. Now the beautiful thing is this: it doesn't matter how many variables you have in your linear system. It has to be one of these three scenarios. You just can't go beyond these three scenarios. So a system of linear equations is either 1, consistent independent, 2, inconsistent independent, or 3, consistent dependent. And it doesn't matter how many variables you have. It's got to be one of these three exclusively. They're all mutually exclusive. So if you have one, you can't have two at the same time, and vice versa. So, okay, so that's how that works. Well, the last thing I want to do is I want to talk about what's known as a general system. How do we mathematically write out a general system of linear equations? And so this is a general linear system. This is how we write it out mathematically. And the way the subscripts work, I'll just make a large version of this. So let's say A2, 3. This number right here represents the row number or the equation number. We'll just call it the row number. And if you want to think of it in terms of columns, this number right here represents the column number. Or you could also consider it the number that indicates which variable or which unknown the coefficient is attached to through multiplication. And so that's what a general system looks like. Well, okay. Hopefully in this lesson what I've done is I've given you a good definition for a system of linear equations. We've talked about what a solution to a system of linear equations would look like. We've talked about consistent versus inconsistent, dependent versus independent, and then hopefully I've also given you a basic understanding of what the general system would look like, how we would write that mathematically, and how the subscripts would work. God bless you, wherever you are today.